Good morning, dear friends. So last lecture we start second chapter, second video. Now in this second chapter of third video, we complete this first topic, that is some important units of measurement, solution and their concentration. So in this lecture we start this chemical stoichiometry. So this concentration units, solution, dilution. So this is the last part of this second chapter, that is chemical stoichiometry. So the stoichiometry, this is a Greek word. This stoichion means element. It's a branch of chemistry which deals with the calculation of combining mass of element. This stoichiometry is defined as a quantitative aspect dealing with mass and volume relation between reactant and product. The symbol of element and formulas of compound stand for quantitative aspects of chemical reaction. This stoichiometry provide brief application to some chemical calculation. So this formulas, this quantitative aspect gives more information about chemical reactions, how to start the chemical reaction, what amount of product will be formed. So all this information is got from this stoichiometric. So in this case we consider this first concept, that is empirical formula. So what is empirical formula? This formula gives the simplest whole number ratio of atoms in a chemical compound. For example, this empirical formula of C2H4O2, C3H6O3, C6H12O6. So these are the three various compound, different compound having different molecular formula. But these three compound have the same empirical formula. That empirical formula is CH2O. This empirical formula is obtained from the percent composition of the compounds. Percent compositions of a compound. It is the ratio of atom of different element in a molecule of a compound. It is the ratio of different elements, atoms of different element in a molecule of compound. So these are the different atoms, three types of atom in three different compounds. Its ratio 1:2:1. This ratio is maintained in these three compounds. So it is a ratio of atoms of different element in molecular compound, molecule of compound. It is based on following points. The ratio of each element is the atomic weight of substance. Ratio of each element ratio is the atomic weight of that substance. Atomic weight of substance. It is expressed by whole number. This ratio is expressed in whole number. The whole number whose shown below is the symbol of element to get empirical formula. This whole number obtained is symbolized in the element to give its empirical formula. So this is carbon having 1 is not shown. This hydrogen having 2, oxygen having 1 1 is not shown. So these are the numbers. So we know the empirical formula. Now this molecular formula. This molecular formula of a compound is indicated actual number of atom of each element. Actual number of atoms of each element present in a molecule. It may same as that of empirical formula. It may same as that of empirical formula. See previous slide. So this is the empirical formula. These three different molecular formulas are there. So this is the actual number of element. These carbon elements are 2 in number. In this compound, this carbon element is 3 in number. This third compound, actual carbon atoms are in 6 in number. So these are the three actual element composition present in molecular formula. So this is the molecular formula, and for this three molecular formula it have the same empirical formula. So this empirical formula, molecular formula different. Sometimes this empirical formula and molecular formula is same. Sometimes it depends upon the number of element present. The relation is expressed as this molecular formula is n multiplied by empirical formula, where this n represent the integer 1, 2, 3, 4. They are like that. If this n is equal to 1, at that time molecular formula and empirical formula are same. This n may be calculated by taking the ratio of molecular weight to empirical weight. Molecular weight to empirical weight. This ratio gives this n number. This molecular formula indicates the different element present in the number and the number of atoms of each element. This molecular formula represents, see this molecular formula. This molecular formula represent number and number of atom of each element. See this molecular formula. This molecular formula gives numbers and number of atom of each element. Molecular formula required the information of molar mass of species. This molecular formula, weight or molar mass. This molecular formula, weight or molar mass of a compound can be calculated by addition of atomic weight present in the molecular formula. For example, this molar mass or molecular weight of SO2 is addition of atomic weight of atoms present in molecule. So this having 1 sulfur atom, 2 oxygen atom. So 1 into 32, that is mass of sulfur atom. 2 into mass of oxygen atom is 16. 16 into 2, 32. 32 plus 32, that is 64 gram per mole. So this 64 gram per mole is a molecular mass or molecular weight. It is called as a molecular formula weight. So this is the actual molecular formula weight. What is structural formula then? So we consider empirical formula, molecular formula and structural formula. So this gives the additional information about the compound. For example, this chemically different dimethyl ether. So this is the dimethyl ether and ethanol. This is the ethyl OH, ethanol. Have the same molecular formula. Molecular formula is same. This number of elements and their composition is same. Their structural formula is CH3O, CH3 and C2H5, that ethyl group and OH attached respectively. See, molecular formula is same but structural formula is different. So this structural formula gives the idea about the compound. These two compounds are different compound, dimethyl ether and ethanol, though it are possessing same molecular formula. So the structural formula is very important. It gives the additional information about the compound. The steps are used to determine the empirical formula and molecular formula. What are the steps? See, first step, a percent composition of element, percent composition of chemical compound is determined quantitatively. So this is the experimental part. From this part we get this percent composition of chemical compounds. This percentage of every element is divided by atomic weight gives the atomic ratio. So this compound containing different element and this percentage of every element is divided by its atomic weight of given atomic ratio. So each element is divided by its atomic weight to give its atomic ratio. This atomic ratio of each element is divided by minimum value of simplest atomic number. Minimum value. We convert that ratio into minimum value. It is called as the simplest atomic ratio. The fractional ratio, if present, if fraction ratio is in fraction, this value of simplest ratio of each element multiplied by simplest integer to get a whole number. This simplest ratio is in fraction, so we convert it into whole number by multiplying simplest integer. This empirical formula symbol of elements are written with a whole number ratio by subscripts. Subscripts are written in the element symbol, below the element symbol. This molecular formula is determined from empirical formula. We know this molecular formula is equal to n into empirical formula. So this molecular formula determined from empirical formula. The simplest multiple is a ratio of mass, molar mass to empirical formula. The simplest multiple is a ratio of molar mass to the empirical formula mass. the molecular formula is always a simple multiple of empirical formula. So we know this molecular formula is equal to n into empirical formula. So this is a simple multiple of empirical formula. What is this simple multiple? This simple multiple is the ratio of molar mass to the empirical formula mass. So see the actual example. So this compound containing 52.2% carbon, 34.8% oxygen, 13% of hydrogen. Calculate the empirical formula mass of the compound. These atomic mass are given. So this percentage is obtained from the experiment. This composition is obtained from experiment. So the solution, first column is element. There are 3 elements: oxygen, carbon, hydrogen. This percent weight is given. We write oxygen percentage is 34.8, carbon percentage 52.2, hydrogen percentage is 13. Then molar mass of atom. We know oxygen molar mass is 16, carbon 12, hydrogen 1. Now we divide this percentage weight by atomic mass, relative number of atom. We get this relative number of atom. So this percentage weight divided by atomic weight, we get this relative number of atom. 52.2 divided by 12, 35, 13.1, it gives 13. Now this ratio of element, relative number is converted into simplest ratio by multiplying by lowest number. So this lowest number is divided by to the same lowest number, we get the 1. This lowest number divided to second, we get near 2, value is 2. This whole number, simplest number divide to 13. What is the ratio given? Is a 6. So this is the simplest ratio of each element. Now we write the simplest ratio of each element in empirical formula. So this empirical formula is showing 3 elements: carbon, hydrogen, oxygen. What is the simplest ratio of carbon? Carbon simplest ratio is 2. We write it subscript. Hydrogen simplest ratio is write in its subscript. Oxygen 1. So this 1 is there. We don't need not show this one. So empirical formula mass. What is empirical formula mass? So 2 carbon atom. So 2 into weight of carbon atom 12, 6 hydrogen atom, 6 into molar mass of hydrogen is 1, 1 oxygen, 1 into 16, that is molar mass of oxygen. So multiply it, add it, and we get this value 46 gram per mole. So this 46 gram per mole is a empirical formula mass. So the stoichiometric calculation. The balanced chemical equation gives the stoichiometry or combining ratios of a reactant and product. When we write any chemical reaction in its balanced state, at that time what it gives? It gives this combining ratios of reactant and product in the unit of moles, and the relationship explain different stoichiometric calculation. So it gives this combination of reactant to form product in balanced chemical equation. It gives a unit relationship between that in the unit of moles. This relation is in unit of moles. To calculate stoichiometry involves 3 steps. First, transfer of known mass of chemical substance in gram into number of moles. First of all, we take gram weight of substance and convert it into its number of moles. This multiply by the factor that gives stoichiometry. In this chemical reaction, this factor is there. So multiply by that factor to give its stoichiometry. And then reverse. After that, this reconversion of this calculated data in moles after completion of reaction, we get this product in the form of moles. From that number of moles, we reconverted these moles into the metric units. For example, the balance equation gives in stoichiometry in moles of reactant and product. For example, 2 moles of NaI aqueous solution combined with barium nitrate, 1 mole of barium nitrate, it gives barium iodide solid, and 2 moles of sodium nitrate. The above equation indicates that 2 mole of aqueous sodium iodide combined with 1 mole of aqueous barium nitrate to produce 1 mole of solid barium iodide and 2 moles of aqueous sodium nitrate. So these are the balancing chemical equation. This relation is in the form of moles units, in the form of mole unit. See this example, calculate the mass of a lead chloride solid is produced when 200 ml of 0.125 molar lead 2 plus ion are mixed with 400 ml of 0.175 moles of chloride ion. Calculate the mass of this lead chloride solid when it produces these ions. What is given? This molar mass of lead chloride is given, molar mass. So this balanced stoichiometry chemical equation is lead ion combined with chloride ion to form lead chloride. So this actual 1 mole of lead combined with 2 moles of chloride ion to form 1 moles of product, that is solid PbCl2. The number of moles, so in this case we convert this mass into actual number of moles of ions. This number of moles of lead 2 plus is 200 ml divided by 1000 into its moles. In that solution that gives 0.025 moles. Number of moles of chloride ion 400 divided by 1000 into 0.175. It gives the value 0.070 moles. From balance equation, 1 mole of lead ion combined with 2 moles of chloride. 1 mole of lead ion combined with 2 moles of chloride ion. Thus, number of moles of chloride required to react. How many moles of chloride is required to react? It is a double than a lead. This lead ions are in limited proportion, that is 0.025. When we double it, at that time this value is 0.05 moles. This much quantity of chloride ion combined with lead ion to produce product. This remaining part of lead, that is 0.02 moles of chloride ions are present in excess amount in the solution, and that part is excess in solution. Do not combine. Why? Because there is no lead ion present to combine this excess amount of chloride. Whatever may be the lead ion present which combine with this much part of chloride, remaining part of chloride ion remain as a unreacted, uncombined. But this moles of chloride is 0.07 moles, which is excess, large excess than required quantity, and thus to produce lead chloride ion will be limited by the amount of lead ion available. This mass of lead chloride produced is 0.04 moles of lead ion and 0.025 into 2 moles of chloride ion into molar mass of lead chloride is equal to 0.05 into, so this double quantity is 0.05 into molar mass. This molar mass is given to 78.10. Multiply that, what is the final answer? 13.9 gram of lead chloride. So this molar mass of lead chloride solid is 13.9 gram. Thank you, dear friends. So in this way we complete the second chapter of analytical chemistry, paper 2. That is the calculation used in analytical chemistry. So in this chapter we have covered the chapter in 3 different parts. First part is a introduction and some important unit of measurement, solution and their concentration. Second part, third part is a chemical stoichiometry. And in this way we complete the second chapter. You should study this chapter simultaneously. Thank you.